Hi everyone, good morning. Welcome to Recitation 8 for Introduction to Deep Learning, and today we'll be covering CTC decoding and beam search algorithms. So in the lecture so far we've seen sequence to sequence modeling. That is when you give your model a sequence of inputs and it generates a sequence of outputs. That is what we generally refer to as sequence to sequence modeling. And we've seen we've seen a general case of when we have order synchronous but not time synchronous outputs. And we've already seen how to train the networks in such a situation. And today we'll talk about what do you do during test time. So what's the meaning of decoding? The process of obtaining the outputs from a sequence to sequence network is referred to as decoding. And there are certain problems associated with it. The first one being, consider for instance that the model generates characters, and one of the decodings one of the outputs that your model generated at inference time was RRROOOD. Now how do you know if this sequence was supposed to be ROD or ROOD? We looked at this problem when we were talking about how to train such a model, the problem of identifying extended symbols or repetitions of symbols. So how do you go about figuring out whether it's supposed to be a repetition of a symbol, or if it's you're extending a symbol in the time? Seems like there's a very simple solution to this problem. All you need to do is introduce this extra symbol that your model generates. We call this a blank and represent it using a hyphen. The only job of the symbol is that it should separate discrete versions of a symbol. So say the model generated RRR hyphen 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 OO hyphen 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 DDD. We'll call this ROD. Everything that is not separated by a blank gets collapsed into a single character. So in the second example, if it is RR blank R, that would be two separate R's. So that is that the character R was extended. And similarly, when it's D hyphen DD, the D character was extended, and so what you get as an output is RRODD. Similarly, the third example. But in order for your model to generate this blank, we need to train the network to learn when it needs to generate a hyphen symbol along with all the other symbols that it generates. So you will add this symbol to the list of symbols that your model can generate that it learns, and then train your network again. So it's very simple. You just add this extra character to the, you remember how at every time step we generate a probability distribution across all the symbols. So it's just one more symbol that your model will generate a probability for at each time step. And just as we did before, we'll construct this graph at training time. And now instead of just having, we were looking at an example of B-Phi during the lectures. So we had B, E, F, and over here we'll just add the blank symbol after every symbol that the model can generate. And it will also, it won't only occur between the symbols, but before and after as well. And then now we have the graph, and we can simply train as before using Viterbi algorithm. We'll calculate the forward and backward probabilities, and get the calculate the error and then back propagate it and train the network, same as before. This is what is known as Connectionist Temporal classification. That is when we allow the model to generate duplicate labels, and the output sequence length is less than the input sequence length, less than or equal to the input sequence length. Coming back to the decoding problem, there was one problem that we talked about. How do you differentiate between repeated symbols and extended symbols? There's one more problem. How do you, when you are decoding at test time, at each time step, how do you decide which symbol to pick? So there are two ways that you can go about it, as we did during training. We can either be greedy about it, and at each time step, we choose the symbol that has the highest probability, and then merge the output sequence that is generated at the end. But this will be a suboptimal decoding because it will only find the most likely synchronous output sequence. The other way to go about it is, what was the objective of a decoding before we talk about what's the other better way of doing it? The objective of decoding this network was to find the most likely asynchronous symbol sequence. So if you're not being greedy about the choice of symbols at each time step, we can pick the most likely, we can find all the decodings that the model can possibly generate and then pick the most likely decoding. But as you guess already, if we did that, if we did all the explicit computations, then it will require for us to do like exponential number of symbol sequences, and it's not practically feasible. So to solve that problem, we have this another idea. We organize all possible symbol sequences in a semi-tree. Now what's a semi-tree? It's very simple and very intuitive. Moving from this slide and onwards, we'll assume that the model can generate only 3 symbols, S1, S2 and a blank. And in this semi-tree, every symbol is connected to every other symbol except for itself, and it is connected to itself through a blank. That is, when S1 is connected to S1, there would be a blank between the 2 symbols. And you can easily identify that there is a very simple structure in this tree that gets repeated recursively. And the key thing to keep in mind is that in this semi-tree, each node represents a unique symbol sequence. Now, how do we decode this graph? We've represented all possible sequences using this tree, but then how do we decode it? Don't be intimidated by the figure on the right. It's actually pretty simple. On the x-axis are the time steps, and on the y-axis, it's the same tree that we saw here. It's just flattened down, and it's represented bottom to top. And it's just the alphas that you see at the final time step, that is x4 over here. Those are the forward probabilities of all possible symbol sequences. And now it becomes very easy. You have basically, if you want to find out the most likely asynchronous sequence, you want to pick the sequence that has the highest forward probability. And over here in this trellis that we see over here, at the end the alpha values are nothing but the forward probabilities of all possible symbol sequences, and then we just pick the sequence that has the highest alpha value. But even though this is the theoretically correct CTC decoder, in practice this graph will grow exponentially very, very quickly. And to avoid such large number of computations and still have a meaningful decoding, we can use pruning strategy to keep the number of computations and the size of our graphs manageable. One such pruning methodology is the beam search algorithm. It is very intuitive and it gives really good results. The idea of beam search is that at every time step, you're going to evaluate, expand all possible symbols that can occur at that time, and then retain only say k number of k sequences that have the highest probabilities. And then you'll move forward to the next step, and again for those k, you'll again expand to all possible solutions, all possible symbols that can be generated, and from this expanded tree retain only those branches, only the k highest branches that have the highest probabilities. Does that make sense? Sorry? Yeah, so this k is called beam width, and it's a hyperparameter. You don't generally go too large because otherwise you'll again start expanding a really large tree. If you make it too small, you might become greedy again. So it's actually a hyperparameter that you can play with. Now to implement this, it can be a little intimidating, but we'll be walking through the pseudocode for this algorithm in this recitation. And you need to keep in mind that throughout, when we are doing beam search, at every time step there will be two arrays, namely the path score and blank path score, that we need to keep a track of as we move from one time step to other. So path score is an array that will contain the scores for paths that will end in symbols, and blank path scores will be an array which will store the scores for all the paths that end in a blank. And we also have a symbol set, which is a list of all the symbols except for the blank symbol. Now we'll break down all the operations that you need to perform for beam search into smaller segments, and then we'll walk through these smaller segments one by one. So first we'll initialize the paths at time t equals to 0, and we've defined a function initialize paths that will do this for us. Then starting from time t equals to 1 till the end of time, we'll first expand the paths with a blank, then we'll extend the paths with a symbol, and then we'll prune the collection of all the paths that we've had so far and retain only the beam width number of paths. And once we are done with all the time steps, then we'll merge identical paths. What I mean by identical paths is there'll be, suppose there's a symbol sequence A, B, C, and there's another symbol sequence A, B, C blank. Now this A, B, C and A, B, C blank are nothing but the same sequence. So to get the probability of the model generating the sequence A, B, C, you need to merge the probabilities of A, B, C blank and A, B, C. So that is what we'll be doing in merge identical paths function. And once we've merged all the paths, now we'll pick the best path. We've at every step been retaining only the beam width number of best paths, and now at the end we'll just pick the paths that has the highest probability, and that will be the decoding of our model for that input. Do you have any questions before we start going through each function?
What is the depth?
The depth of? So you will be you'll keep on checking for the symbols for every time step. Beam width is at every time step how many paths do you retain after every time step. So you could be expanding all possible symbol sequences, but because that is not computationally feasible, at every time step you will say beam width is k, you will preserve only k best paths and drop everything else. And then at the next time step, you will expand these k paths further and then retain only the k best paths again, and keep doing this for every time step.
And what is the termination?
The number of time steps that you have to generate the output for.
And that's speech to speech?
Sorry?
That's speech to speech?
So say you are doing speech to text translation, then you would have an end of sequence tag. So when you encountered the end of sequence tag, you know you have to stop. So when your model generates the end of sequence tag, you know you want to stop. This is for inference. We are talking about CTC decoding. So we've already covered how we train the sequence to sequence model. We've looked at multiple ways and we figured out that Viterbi is the best way to go. And now we're looking at how we decode it. How do you evaluate your model? How do you generate the output from your model at inference time? Now I'll start going through each of these functions step by step. So first we'll look at how do we initialize our paths at t equals to 0. So we'll try to understand what's happening in this trellis. It looks complicated, but we'll walk through it and we'll understand it. So as I said that there are 3 unique symbols that we are working with in this example, the blank, S1 and S2. So if we are initializing all paths, our paths can begin in a blank, it can begin with the symbol S1 or S2. So these are the 3 paths that we'll be initializing. How we'll do that is, this function is going to take in as input the symbol set, which was all the unique symbols that a model can generate except for the blank. Y here is the probability of generating any symbol at time t equals to 0, and beam width is how many of these expansions do we want to retain. So first we'll be dealing with the blanks, and then we'll be dealing with the symbols. So because we're starting off, we have nothing so far, and if we are just adding the blank, then Also keep in mind that we were maintaining a path score and a blank path score. Path score is going to have all the scores for the paths that end in a symbol, and blank path score is going to have all the scores for the paths that end in a blank. So because we are adding a blank right now, we'll update the blank path score with the blank symbol and its corresponding probability. And then we've created this set initial paths with final blank, and we'll just add a path to it. So after we're done with this step, if initial path with final blank is this, we have the blank symbol in it. Moving forward, now we'll go through all the symbols that we have one by one, and then add this to the initial path with final symbol set. So it's pretty, so say on the right hand side of the slide, this figure that we have, it would be empty at the beginning. Then we'll take a symbol, we'll put it in this, and we'll update the path score array with the score of this particular symbol. And yeah, we'll keep doing this for each symbol in our symbol set. And when we are done with this, we'd have initialized all possible paths that we can start with. We've gone through all the symbols that we can begin our trellis with. Any questions? Okay. Moving forward. So once we've expanded all paths in the initial, once we've identified all possible initializations, we'll prune it. We'll retain only the beam width number of best paths and drop everything else. Yeah, so this is initialization. You're just we are going to step through it. Yeah, this is how you like what all possibilities can your paths have at the first time step. It can be all the symbols or a blank. So we added that, and we then retain only the the beam width number of best paths and dropped everything else. Now we'll go through each time step. And the first thing we'll do is we'll extend the paths with a blank. So now we'll take a look at this symbol, at this function. So we could have had a blank, an S1 or an S2 symbol at the when we initialized a trellis, and now we are extending it with a blank. So you can go from a blank to a blank, from S1 to a blank, or an S2 to a blank, right? And then at the next time step, you could go from, you could stay from a blank within a blank. You could have gone from a S1 to a blank and then stayed within a blank, or you could have gone from S1 to a blank. Similarly for S2. Then again at the next time step, you can you can keep extending these paths, so on and so forth. And we'll look at how we do this through a code now. It might make more sense. So the first thing we'll do is again look at the blanks first, and then we'll look at the symbols. So you created this container called updated paths with terminal blank, and does this so if you are adding blank after any particular sequence, essentially the sequence remains the same, right? Because it's going to all collapse into and remain the same sequence. So when you're extending a path with the blank, you just check whether this container already has this path that you're iterating, and if it does not, you add it to the container, and then you update the score for that corresponding path in the blanks path score array. And because you're not, even though you're not changing the sequence, but you're changing the final probability of this particular path now, because you've added one more blank to it. So you update its score. And you do this for every symbol in the paths with terminal blank list that you had. So for our particular example, at time step 1, all the symbols that we were working with were a blank, S1 and S2. So paths with terminal blank would only have had a blank for us at time equals to 1. And so when you're done with this updated paths with terminal blank will only have a blank symbol in it. Now we look at all the paths that had terminated in a symbol. So we'll check if this path already exists in the updated paths with terminal blank container. If it does, then we'll update its score again. Because we picked this from the paths with terminal symbol, because we got this path from paths with terminal symbol, that means its score must have been in the path score array, the array that had the score for all the paths that ended in a symbol. So we get its score from there, and we update it because we are extending it with a blank, we update its score, and then we update the final score in the blank path score for this corresponding path. Did that make sense? Okay, I'll try again. So this function takes in as an input two different path values. The first path is the paths that end with a blank, and the second list contains paths that end with a symbol. And you also have scores for all the symbols at this particular time step when we are evaluating, when we are executing this function. So first, we'll only deal with the paths that had ended in a blank, and then we'll move to the paths that were ending in a symbol. So first, let's look at the first snippet of code. The first snippet of code. Is this clear that when we are extending any sequence with a blank, the sequence essentially remains the same? The sequence does not change, but its score does, because you've added a blank to it, so the probability of the forward probability of the sequence has changed. So you calculate the new score for this path, and because this path had a blank at its end, you would find its score in the blank path score array. So you would go to that. Basically, we are using the path to identify the blank path score and path score arrays are. You can find the score for any particular path in these arrays using the paths themselves. That is how you should structure your code. So you will find there would be a score in the blank path score array for that particular path. You will just update it with this new path score. A new score that you calculated, and you will do this for every path in the paths with terminal blank list. Is it clear now? And now we'll do something very similar for paths that ended in a symbol. But now, if your path had ended in a symbol, if that even though you're adding, like I said before, even though you're adding a blank after this particular path, the sequence still remains the same, only the score will change, right? The forward probability will change, but the sequence, the compressed sequence won't change. So, but this particular path that we are looking at right now came from the list paths with terminal symbol. That means its corresponding score would be in the array path score over here. So we get its previous score, we multiply it with the probability of the blank, and then we update the score of this path in blank path score. And if this particular path had not been in the updated paths with terminal blank, we will add it to this set, and then we'll update its score. So for the particular, if we are just looking for blank S1 and S2, at the end of all the operations in this function, our updated paths with terminal blank will contain a blank S1 and S2. You would have added a blank when you were done with the first part of the code, and then you would have when you were iterating, if you did if path in update, when you were doing for path in path with terminal symbol, first you would have encountered an S1, and that would not have been an updated paths with terminal blank. So you would have added it to this set over here, updated its path in in blank path score, and then the next time you would have come across S2. Again, that would not have been there in updated paths with terminal blanks. You would have added that and updated its score. And because these are the only symbols we are looking at, and this is time step 1, we'd be done with this. Now, once we are done with extending our paths with a blank, we'll extend our paths with symbols. Very similar operation. But now when you're adding symbols, your sequences will change. So you can go from a blank to S1, from blank to S2, from S1 to S1 or S1 to S2, from S2 to S1 and S2 to S2. When you are going from time t equals to 0, all your initial paths, when you extend them with a symbol, then in this particular case, all of these things can happen. When you go from time step 1 to time step 2, again you will be extending everything with all possible symbols. And similarly, you would be doing it at each time step, and this graph is going to grow vertically as well. And now we look at how we do this through the code. It's a very small difference, but because earlier when we were adding a blank at the end, that did not change the sequence, but now since we are adding a symbol, it will change the sequence. But if we found a path in the, so this time when we're writing the function, we'll first look at the symbols that ended in a symbol, and then we look, first we look at the paths that ended in a symbol, and then we look at the paths that ended in blanks. So if when you are looking at a path that ended in a symbol, you'll iterate through all possible symbols that you can add, and if the symbol is same as the symbol at the end of the path doesn't change, right? If you had A, B, C and you're adding C again, then C and C will collapse and remain just A, B, C. So you update, the path does not change, but if the symbol that you're adding is not the same as the symbol at the end of the path, then you will add this new symbol at the end. So say it was A, B, C and now you're adding an A, so the sequence will now become A, B, C, A. So you update your path, and then you add this new path that you've computed to this container that we've initialized, updated path with terminal symbol, just as we did in the function before, and then we update the scores for these paths with the probability of the score that you are adding to the sequence. So after we are done with all the paths that ended in a symbol, now we'll go through all the paths that ended in a blank. This time, again we'll pick a path, we'll go through all the symbols, and because we already have a blank at the end of our path sequence, at the end of our symbol sequence, we need to add a new symbol to it. Because say if it was A, B, C blank, even if we are adding a C, we know that we want to extend a character. It is not the repetition of a character or a symbol. So we update the new path, and we check if we already have this path in the updated paths terminal blank container. If it does, then we simply update the score of this path. If it did not exist, then we add the new path and then update its and then add its score as well. And we do this for every symbol for every path in the paths with terminal blank list of paths. Yes.
I understand why we're not repeating times, but why are we avoiding the cases with the repetition of characters?
So because you came in a little late, we discussed why we add blanks. So suppose when you're decoding at test time and your model, I'll quickly go back.
No, I understand why we're adding blanks.
Yeah.
Avoiding repetition of characters.
To understand why we are avoiding repetition of characters, you need to see this. So suppose at inference time a model generated RRROOD. How do you know if it was supposed to be ROD or ROOD? You need to know whether a particular reoccurrence of a symbol was extension of a symbol or the repetition of a symbol. Both are different things, like we saw in the lectures. So to understand whether it was, to figure out whether it was an extension or a repetition, we introduce this extra character blank. If two characters are separated by a blank, it is an extension, and if two characters are not separated by a blank, they get collapsed into the single character. Okay? Coming back. Okay, so we have extended all our paths with the symbols now, and now we have, at any particular time step, we have expanded all possible symbols, we've expanded all possible paths, and now we'll prune it to retain only k best paths. the beam width number of paths. So first we'll gather all the relevant scores, the scores of the paths that ended in a blank and the scores of the paths that ended in a symbol, and then we'll find a threshold threshold for the score that would retain only the best beam width number of paths, and then we'll go through all the paths that ended in a blank, and if its score is greater than the cutoff, we'll keep it, otherwise we'll drop the path. And we'll do the same thing for the paths that ended in a symbol. And now we started off with all possible paths, but we have retained only the top best k paths. Both kind of paths, the paths that would have ended in a blank or the paths that would have ended in a symbol. We would do these operations repeatedly for each time step, and by the end of it, we would have retained the best at every time step, because we were evaluating all paths but retaining only the k best paths. When we are done with all the time steps, we would still have k paths, and they would be your optimal decoding sequence would be one of these paths. That makes sense, right? Now we'll merge all the identical paths. What I mean by identical paths is that if suppose the sequence was ABC and ABC dash, both of them are essentially identical. So to calculate the total score of the sequence ABC, we need to add the scores for both of these paths. That is what we'll do in merge identical paths function. So we'll go through all the paths in the paths that ended in terminal symbol, and we'll just take their scores, and then we'll go through all the paths that ended in a blank, and if we already have this path, then we'll just add the scores of both the paths, otherwise we'll add it to the set, and then do this for all paths, and by the end of it we would have combined all paths that can be merged. Make sense? Doubts? Okay. So now we have decoded at all time steps, retained the best paths, merged all the paths that could be merged. Now all that's left to do is pick the best path, the path that has the highest score. So we'll just in the final path score, which we get from the merge identical paths function, we'll find the index of the path that had the highest score, and then find the path, and then we can just find the index into the paths that we had and get the best path, and that would be the decoding of a model for that particular input, the best decoding that a model can generate. That's all for beam search. Now Louis will be covering CTC decoding. That will help you in homework 3 part 2, and you will be implementing beam search in homework 3 part 1. So you can refer to these slides when you are implementing your code. Yui? Do you guys have any questions? I have my connector already.
Okay.
So I will talk about how to use the CTC loss software. The implementation of CTC loss in PyTorch that you definitely will use in homework 3 part 2. So actually for training and inference, we have to use 2 different libraries. So I will introduce both of them. For training, in the past semesters, we use a third-party library called warp CTC. But since starting from PyTorch 1.1, it comes with a built-in loss function called nn.ctc loss. So for this semester, we strongly recommend you to use nn.ctc loss and not any other third-party implementation. To demonstrate how to use this one, we start with a toy task called English spelling and to pronunciation. So here's some data. One thing that is interesting for this data is that for the phonemes list, we start with a space. Why is that the case? That's because when decoding with CTC, we have a special symbol called blank or empty. So we have to represent it because our model. So let's say we have p different phonemes, as I said here. We will have to the model output of our model at each time step must classify into p plus 1 classes, which is the empty symbol and all the phonemes. So accordingly, so by default, nn.ctc loss and the decoding library we will introduce later use index 0 as the blank symbol. So we should put our phonemes into index 1 to p and reserve the 0 for the blank. So this is basically we do some data pre-processing and define our model. The model itself is just very simple. But the thing that is important is in the data pre-processing. So we're gonna say X here. X means the source sequence and Y means the target sequence. So X here is the sequence of letters of our word, and Y is the sequence of phonemes. But here we can see that the X and Y is actually proposed in a different way. You can see here, path sequence. X is path sequence, but Y with an extra argument called batch first equals true. Why is that the case? And you can also see their shape is different. So this seems really strange, but why is this case? That's because nn.ctc loss has some very unconventional requirements to its parameters, which we will cover just now. So as always, PyTorch comes with every model comes with its official documentation. So if you're writing your own program and you have any questions, you should always refer to the official documentation first before you ask a question on Piazza or something. So nn.ctc loss takes 4 arguments. So yes, these are very kind of specific. They have very specific requirements, so be very careful. Many of them are that you will not match in other places in PyTorch. The first argument is called log probs. As suggested by the name, it should be a log probabilities. However, in the past, our model, like in homework 1 and homework 2, our model doesn't output log probabilities. It outputs logits. Logits is the number you have before the softmax. But here we have to use log probability, which is the number after the softmax. So you have to add a softmax layer after your model. So if you provided probabilities or you provided logics, it will not work. So we can see here our network is here. We have the last line here. So notice this one. So log softmax is converted. So self.output, this is a linear layer. So self.output out, this will be our logics. So we must convert our logics into log probabilities with log softmax. 2 is the dimension. Means you go through the dimension with index 2, which is the last dimension, or the class's dimension. So in this way, our output here is log probabilities. So the second parameter, second argument is called targets, which is just your targets. However, this is very special. That its shape is different from the convention of a PyTorch. The shape is n to s. So n is the batch size, and s is the sequence length dimension. But in PyTorch, the convention is to put the times dimension in the first and the batch dimension in the second. So this is the reverse of that. Yes, I have never seen anywhere else in PyTorch that have these requirements. So to get the shape that fits with this one, if you use pad sequence to pad your target sequence, you must explicitly set batch first. You must explicitly set batch first equals 2. This is default to false. If it's false, the output shape will be time step first, batch second. So if it's true, it's batch size first, time step second. This is required for this one. And yes, also you must be careful that the index of phonemes must not contain 0. It should be 1 to p. So the third one and fourth one is the length of input and the ground truth. People also have problems with the third arguments in the past. So you'll see this is the length of the log props. So I must stress here that this is not the same as the length of the input of a model. Yes, people use different models, but sometimes because for homework 3, we have one utterance. So each utterance have probably hundreds or thousands of frames. So in homework 3, we will use this as a whole sequence as input. So this is very long. Many people try to make it shorter with CNNs or pyramidal RNNs. This will make your output length different from your input length. So your network should correctly compute the length of its output and use that output as this parameter. We can see here in our code, we didn't change the length, but we still you can see we output not only the prediction probability, but also the output lengths. This is, I would recommend whether your network change or not change the input length, you output the output length. Because at some time in the future, you may want to change it. And if you didn't notice this one, you will have a hard time debug this one. Many of people have suffered from this last semester. So please be aware. And there's nothing much to say about the training. This is very standard. Once you have all once you have all your inputs in the correct shape and correct values, it's just a very simple training. Yes, there's nothing much to say about it. So training. Wait, what's going on here? Restart. How to restart? So we can run it through again. And yes, you can see this is training very fast. So this is for the training. For decoding, we use completely different things. We use a third-party library called CTC Decode. So its installation. So I will not demo here because it's not very interesting. You should just follow the command here. This will be, as usual, this will be uploaded to the website shortly after, so you can follow this to install yourself. And this is a very simple test to try whether you are correctly working with your CTC decoder. It should output a 1. This is correct. Sometimes it crashes, has some errors. So you should work with it. So for the CTC decode, so CTC decode sadly has no absolute zero documentation and zero command in its code even. So you have to. So if you try to read source code, it will be pretty painful. So yes, this caused a lot of issues in the past. So we basically provide a simplified documentation here that we think these arguments will be useful for our homework. There are actually more arguments, but well, either we don't know what it means or it is unrelated to our homework. So for the constructor function, the first argument is named phonemes. But actually this parameter is not used in the code. The code is just check its length and didn't use the string in it. So this is very strange, but you still have to obey with that. It requires it to be a list of characters, or character is just one strings with length 1. The length of the list must be the same as the number of classes, which is the number of phonemes plus 1. Other parameters are pretty much self-explanatory. So for decode, we can see here, this is similar to the CTC loss function. However, this shape here, again, this is different from what you use in CTC loss. So we can check here earlier. So the shape here is TNC. However, in CTC decode, the shape is NTC. So what you need to do is to transpose it before the input. The length, this is simple. So for return value, it returns 4 values. But actually, we only need 2. The other 2 is we don't find it has any meaning in our homework. So the first item of the output is a decoded top sequence. So it not only output the best sequence, it output all the all sequences found in the beam search, which is the number of beam width. So the shape is like NBT. However, in the B dimension, we only need the first, because we only need the best sequence for evaluation, we only need to take the 0th index in this dimension. And this is the same for the output sequence length. We can see here we have some code. The first block is just visualization, you can ignore it. So in the second we have some test data. And some data preprocessing this is the same as the one we use in training. So yes, we can see here, we have to do a transpose. 0, 1 means, transpose 0, 1 means you swap the 0th and 3rd dimension of the tensor. So after that, we get the output and the lengths. So we first visualize it. Visualizing, we does not use Y for visualization. The best sequence here, we get the guess the best sequence out from the decoding. So here I is the the index of sequences in the batch. So the first dimension here you can see the first remember that the output shape is NBT and NB. So the first dimensions are N, which is the batch dimension, I. So the second one, as we said before, we only need the best one in the beam, so it's 0. So the first one, this expression means that we only take the first, the first few symbols whose length is the same as the test, the length is length, the length of the ith output sequence. So for this, we get a one-dimensional tensor that contains the best sequence, and then we transform it into strings and print it. The result of this one is, so again, we come back to our task. Our task is, you remember, this is English words to pronunciation. We can see its result here. We add some visualization. We can see actually the test accuracy here is 100%. You can see how it works. T. So this is correct. How it works is that if we see two E's, it predicts both of them as E. So these two, when you CTC decode, these two merge into one symbol. So the output is just E, T. So yes, this one gets wrong. I don't know why. This sometimes wrong and sometimes correct. This is really strange. So the third and fourth are always. So you can see the third one is also interesting. Sign, S-I-N-E, sign. So one thing interesting here is that it predicts the E in the end into empty. So we know if English word ends with the consonant and E, the E is not pronounced. So it correctly predicts E as an empty symbol, and it doesn't appear in the output sequence. And I here, actually, it knows that because there's an E in the end, this is called an open syllable. So I is pronounced as I, and it predicted correctly. And the last example sent is also predict the pronunciation of every character correctly. There's some caveats that I'm kind of collecting from other people. It's an incomplete list. We will add more caveats and FAQ when our homework 3 part 2 is out. So for now, one thing that is really annoying is that CTC decoder does not have any error, exception or error processing built into it. And its main function is all written in C++. So if a C++ finds something wrong, it will not throw an exception. It will just crash, segmentation fault, core dump. So this is very bad for a Python program because Python programs never expect to do that. So if your CTC decoder gets wrong, it will crash. Your program will crash silently. You didn't know what goes wrong. You just see your program stops. So this is very annoying. We will suggest you to print out all your parameters, shape, and content before you run a decoder. So you make sure that, yes, I mean, you at least you add a print here. When you are developing, add a print before you decode. Otherwise, you don't know what you get wrong. And if you really get wrong, check again with this documentation we provide to see whether you fulfills all requirements written here. If you try to run this here, it doesn't crash. So what's wrong with here is that our phoneme size is 2, but our input has 3 classes. So this is class mismatch. This will cause a crash. I read the C++ code, they have a kind of a assert for this. If the assert failed, the C++ program will just crash. So here, you can see this is keep running, still keeps running. Actually, the C++ program has crashed, but the Python doesn't know it. So it thinks it's still running, and it freezes. So this is very bad. Don't try this at home. You can try it on, Google Colab. So, so yes, this is all of our demonstration here for the CTC coding. And thank you.